Hola a todos, mi nombre es Anton Shirshov, soy ingeniero de petróleos con 18 años de experiencia y en este video yo voy a hablar sobre el tema de geonavegación de pozos horizontales. Es un tema muy interesante y importante y para mejorar la calidad de entrenamiento yo tengo que cambiar a inglés porque mi nivel de español no sería suficiente para este contenido complejo. Okay. So we are going to our agenda. So we're going to start from the introduction to geosteering to understand what is it geosteering and why do we need it. Then we move to the errors and uncertainties while drilling horizontal wells and going to be reviewed two groups of uncertainties, geological uncertainties and geometrical uncertainties. Then they move to geosteering methods themselves, starting from the basic ones to the most advanced. So we start from the geosteering using non-azimuthal measurements, then they move to geosteering using azimuthal measurements and LWD images, and then we go into geosteering using deep directional measurements, which is the top technology at the market this time. So after that, we will talk about how geosteering can help in updating 3D geological structure model in real time or finally post-job. And then they move to the practice. So I'm going to open the real-time geosteering software and will demonstrate some tools and techniques inside the geosteering project. And the final topic is LWD and directional drilling as a part of geosteering. So we're going to cover the mud motor rotary steerable systems and the logging while drilling. So if you don't have, especially if you don't have a background in drilling or directional drilling, this topic will be very useful to refresh because we're going to refer to these technologies during the training many times. Okay, so let's move to the content. So introduction to the geosteering. First of all, what is the difference between geosteering and geometrical drilling? So geometrical drilling is the approach when they drill horizontal well according to the plan without any changes. For example, here we have our formation target with the thickness of 4 meters. And now we're going to plan this well using the geometrical approach. So first of all, we create our target, which is T1, the landing point, T2, the point of building up the 90 degrees, and the T3, which is the end of the well, right? So using these geological targets, the drilling engineer will create the plan, and the directional driller on the rig will follow the plan. And in theory, right, if the model was accurate enough and the planning was good enough, so finally we have to end up the picture like this, as you see right now. But and how the first horizontal wells were drilled actually many years ago. But industry very quickly realized that the actual environment which we're facing during drilling the horizontal well most of the time is not the same what was planned, right? Like in this case, we have a deep change, and you see the drilling as per plan without any changes would lead us to lose the significant part of horizontal well outside of the pay zone, which will lead to the decreased production and increased cost of the well. So in this case, the right approach would be to adjust the trajectory in real time based on the actual environment we see during drilling. So for this, we would need, of course, the logging while drilling, the measurements while drilling methods, and the directional drilling. So, but the big question here is really if we had an accurate geological model and if we had the good planning and everyone did everything right, why do we have this problem at the end of the well, right? So, who fault is this or what was wrong? So, and actually, we move into the big topic here, which is called the errors and uncertainties while drilling horizontal wells. So there was no fault from anyone. That's just a limitation of current technologies and methods used in drilling horizontal wells. And let's talk more about this. So there are two big groups of uncertainties. One is geological uncertainties, which is related to the geology and the Earth itself. And second is the geometrical uncertainties, which are related to the well itself, to the well trajectory and how we drill the well. So in the first group, it's of course the structural uncertainties in the true vertical depth, and starting from the seismic resolution. So as you know, currently the seismic resolution is from 5 to 10 meters accuracy, which means the formations were identified during the seismic interpretation by default having this plus minus 5 to 10 meters, right? So of course it will be adjusted based on correlation, but correlation brings the different source of uncertainties, which called the deep uncertainties. I'm going to show you in the next slide. So this can be caused by different perception of regional, local, and micro dips, and some errors during the identifying and correlating the well tops. And of course, the lateral changes. So in lateral changes, we mean subseismic faults, the faults which have just few meters in the in amplitude, so you don't see it in the seismic, and some lateral changes like facies changes and etc. So all this is the providing the uncertainties from the geological side. Also, we have the geometrical uncertainties, so which related, as I said, to the well itself, because the well and trajectory of the well and the tools which are measuring the trajectory, all of them have this uncertainty. And the resolution of this uncertainty, it can reach a few meters as well. So it's affecting us the same as the geological uncertainties. Even it's not not easy to notice. We're going to review it in the next slides. So the main two errors or source of errors are MWD survey errors and the trajectory interpolation errors. So let's look into details. First, starting from the deep uncertainties. In this picture, you see two offset wells, for example, well number 1, well number 2, and we have few kilometers between the distance between these two wells, right? And if we try to correlate the regional deep between these two wells, it will have some value, right? According to this structure. But using the same structure, if we try to calculate the local deep, like in the range of hundreds of meters, it will be different. So the average is different, right? And if we start to look at the like 20, 30 meters resolution, it will be so-called micro deep, which actually we can calculate only based on the images or deep resistivity tool or accurate correlation in the geosteering software. But the problem is, while drilling horizontal wells, which has the lateral section few hundred meters, right? So first of all, we are working with the local and micro dips, but the global geological model normally gives us the regional dip. So, and this difference between those two can bring us this uncertainty drilling the horizontal well. So now let's do a little exercise. So let's see how really sensitive the horizontal well to the changes in the dip. This is the case for you. We have a reservoir which thickness is 3 meters, and we have to land the well 1.5 meter from the top. So we have to land it and drill exactly in the middle of this formation. So the well duration is 650 meters, right? So is what was planned. Now we move into the, and of course is important, we expected to have the flat dip, which is 0 degrees. And now we move into the actual case, and we see that the dip has changed for some value, right? We don't know how much, but it has changed. So, and now this is the task for you to calculate. So considering the dip has changed and we lost exactly 343 meters, this part here, we lost 343 meters out of 650. So now is the task for you to calculate. So how much this dip really changed to bring us this, I would say, catastrophic result, because almost like the half of the well is out of the pay zone, and probably that's in real life going to be a sidetrack and redrilling of the well. Okay. But before moving to the calculation, I just want to do some disclaimer. Please don't be confused with the scaling, right? Don't try to understand that how much this angle just by looking at the curtain section, because for example, this curtain section we have the we have the ratio like 1 to 70. So for the 10 meters in vertical scale, we have almost 700 to the horizontal scale, right? So, and working with the geological section, we can zoom it in many ways. So, for example, we can put it is the like this, right? In this case, it will be ratio 1 to 40, for example. In this case, it will be 1 to 2.5, and in this case, to 1.5, right? Which we cannot see almost anything, which actually is close to the one-to-one resolution, but it's absolutely useless for the geosteering engineer, right? So, okay, so having that in mind, now let's move to the calculation itself. So please open your calculators. You can pause video here, do some math, and then go back to see the result. So, and I'm giving to present it right now. So the change in angle, which caused us to lose 343 meters in the shale, was just 0.26 degrees. So you can calculate and check it by yourself. So that small change was the problem of losing almost half of the horizontal section outside of the pay zone, which in real life probably would cost a sidetrack or abandon of the well, right? So the conclusion here is the long horizontal section. By long I mean a few hundred meters at least, right? And with the thin formation, which is few meters in the formation, so they are very sensitive to any change in the deep, in the formation deep. So any changes like few decimals of changes less than 1 degrees can be catastrophic for the horizontal well if not apply the changes to the trajectory. Okay, so that was one example of the of one of the biggest geological uncertainties. And also, as I said, we can expect to have some subseismic faults. We can have some lateral changes of facies, and etc. etc. So the uncertainties which coming from the geology and the methods are significant. And now let's move to the geometrical uncertainties. To better understand how horizontal well is sensitive to any changes to formation deep, let's do a little research here. So for example, let's make the parameters. So this red line is our reservoir top. This is our horizontal trajectory. L is the length of the horizontal section in meters. Okay, and the Y is the angle in degrees in which potentially formation can have a change. Okay, so and how many degrees it's possible that formation will change during the drilling. And the delta TVD is the difference in the true vertical depth which we will have at the end of this angle change. So, and this parameter we will call the horizontal well sensitivity to the formation deep. So just this delta TVD is our parameter called sensitivity. Okay. Now let's do research and let's make a table to calculate the sensitivity for different lengths of the horizontal section and different angles this way. And let's have a look how different horizontal wells sensitive to the deep formation changes. So in this table we have all the calculation done. So in the vertical axis, we have this angle in degrees. So starting from 0.1 till 5 degrees. So going down is decreasing the angle of the formation. And on the horizontal axis, we have the L, which is the length of the horizontal section. And the parameters, calculated parameter will be delta TVD, which is our sensitivity. Okay, so and let's make the gradation. So let's say if we have sensitivity less than 2 meters, we will color it in blue. So it's kind of the minimum sensitivity and fairly acceptable. If we have sensitivity from 2 to 5 meters, So it's already significant, but it's still okay. We're going to color it in green. Sensitivity from 5 to 10, it's already critical because depending of the geology environment, so it can be already bigger than your formation target. So we will mark in a yellow flag. And sensitivity from 10 to 90, we will mark as the red. So that's the critical difference. And this obviously will lead your horizontal well to be out of the pay zone, definitely. And let's have a look at our research calculation. So now you can on the example of one well, see how it's working. So for example, if our horizontal section is just 600 meters, which is not that long, the typical horizontal section, and if we believe that formation can vary plus minus 0.5 degrees, in this case our sensitivity is 5.2 meters. So which means if the angle will change to 0.5 meter for this horizontal section 600 meters long, by the end of the well we're going to have this difference in TVD. Okay, let's look at it again. 0.5, 600, and 5.2. And now you can find any of your wells which you're working right now on your project or from your previous experience and see how was it sensitive. For example, if we have, let's say, horizontal section 1000 meters, which is 1 kilometer, and you can see that it's getting to the green to the yellow zone of sensitivity after 0.3 degrees. So which means every changes in 0.3 degrees is already bring us to the risk area. And if you look again to the entire table, you can see that the most of the wells are in the green or in the yellow or in the red zone. So which means for most of the wells, by default, even with the calm geology, like from the marine sands, which don't have much fluctuation in the deep, like just plus minus 1-2 degrees, can be decimal degrees, and the horizontal section less than kilometers, they almost all of them here in yellow or red zone. So which again proves the concept that it's very risky and it's not efficient these days to drill such horizontal wells geometrically, just following the plan without any changes in the in any adjustment in the trajectory, without doing geosteering. And we're not even talking here more than 1 kilometer. So obviously, if you extend this table and we'll consider the horizontal wells with the lateral section, few kilometers, 2, 3, and more kilometers. So obviously there is no safe zone even for this well. So every change in the deep is critical, and you need to have the geosteering technologies and the services applied in this well. So no geometrical drilling. There is like it will be the catastrophic to drill this well geometrically with such a long horizontal section. So the biggest source of errors here will be the MWD survey error. So as you probably know, every MWD tool, it has an error, right? While taking the survey, it has an error. It's about 0.1 degree in inclination angle, and it's about 1 degree in the azimuth. So, and as we go deeper, these errors accumulating, making in the space the shape called so-called the cone of uncertainties, right? So, and if you calculate in any directional drilling software, you can do this. If you calculate the actual size of the cone of uncertainties, so sometimes it will be a few times bigger than your target. For example, for this well, which is like almost 3,500 meters deep, right? If we calculate the cone of uncertainty, so at the TD, it will be almost 2 times bigger than the size of the target. So, which means with the different probabilities, the well can be anywhere inside this cone of uncertainties. So, if we let the well being drilled geometrically, So statistically, it can end up in any part of this cone. So it can be inside the pay zone or it can be outside the pay zone, right? So that's why, again, this error is bring the significant impact on the accuracy of the horizontal well. The next one is even more subtle, so you almost cannot see it. It's called the trajectory interpolation error. So for more details, you can refer to some publications like this one. And also, if you don't have a background of drilling, I suggest to review the drilling part and then get back to this slide again. So the current industry standard to calculate the MWD survey is called the minimum curvature method, which assumes that the arc between two surveys has a constant radius of curvature. Let me show you here. Okay, so that's the assumption of the current calculation method, that between two surveys the arc has the constant radius of curvature. But actually, especially if you drill with the mud motor, during the slide mode your radius is less than the calculated one, and if you in the rotary mode, the radius can be more than the calculated one. It creates some curvature on the well trajectory, which you cannot see in the calculations because it happens between the surveys. So you get survey number 1, survey number 2, and what exactly was happening between them, you cannot see it on trajectory unless you run in some advanced survey calculation methodics like high definition surveys or something like that, or unless you're looking at the continuous inclination and to see what's going on between the surveys. Okay, and let's do this little exercise to estimate how much impact can be done by this trajectory interpolation error to our horizontal well. For example, imagine that you have to drill a horizontal well. It's purely theoretical exercise, and build up equally the inclination from 0 to 90 degrees with the constant dogleg 3 degrees per 30 meters. Okay, so and imagine your BHA, which is close to the real case, give you 9 degrees per 30 meters in dogleg. So which means like simple directional drilling calculations telling you that you have to slide about 30% of the time. So 30% of the time you drill in the slide mode and 70 in the rotary mode. And in average, during that interval, 30 meters interval, you will get the dogleg severity 3 degrees per 30 meters. Okay, so and actually if it doesn't matter in terms of calculation, if you start to slide first 10 meters and then 10 meters rotary and 10 meters rotary, or you can do it in the middle or you can do it at the end. In all three cases, the static MWD survey will show you the correct angle, and it will show you the dogleg severity 3 degrees per 30 meters, right? But let's have a look if there are any difference actually if we do this sliding in the first, middle, or the end of the interval. Okay, our 30% of slide. So which means 10 meters out of 30 we're going to drill in a sliding mode. Let's go. Okay, so once again, our task is to slide 10 meters out of 30 meters to get an average 3 degrees per 30 meters in the dogleg severity. And now we have 3 drillers here. And let's imagine the first driller just slides first 10 meters and then 20 meters he drills in rotary mode. The second driller, he slides in the middle. So 10 meters, first 10 meters he drills in the rotary mode, then 10 meters he slides. You can see it here, right? And then he slides, and then he has in rotary mode again, right? And the third driller, he slides only the third interval. Okay, so in average, they all get the dogleg severity of 3 degrees. So now let's have a look if any difference in calculations. So actually, the first driller will end up by the end of the well 10 meters above the calculated line, just because he was sliding the first interval out of 3. The second driller will end up like 90 centimeters above the calculated line, which is almost exactly at the point. And the third driller is the 10 meters below. But this exercise is not about to make a conclusion which interval is better to slide or not. This exercise is to show the impact of the slidings. And in the real environment, the directional driller slides the intervals like based on his calculations, based on his experience, and based what the BHAs let him to do, right? So, but the sensitivity of this error is you can see here is in the range of meters. So it's not centimeters, it's in the range of meters. And this is an interesting case being published now. This is the real well, which was drilled with the mud motor with the in somewhere in Africa. So you can check more details if you want by referring to this paper. But briefly, so what was happening? So you can see here the inclination. So the directional driller building up inclination from almost 60 degrees to 90 degrees. Okay, and this is the measured depth of the well in feet. So we have about 1,000 feet here, which is about 300 meters, and we have the TVD here. So the yellow squares is the static MWD service. So till this moment, the static MWD service is the industry standard, and this is the one which goes to every model, every report, everywhere, right? So what's going on between this the static service is only stays in the curve, so it's not been considered in the calculations. So these red circles is the continuous inclination, okay? Continuous inclination, and this purple is the tool face, so which means wherever you see the purple points here is the sliding mode. So he's sliding. So and now it's quite obvious what's going on. So the directional driller slides in the second interval of the pipeline, right? So the natural tendency of the BHA is to drop the angle, okay? So if you like to drill in rotary mode, you see the angle drops. And what he does, he building up. So he does exactly the right thing, right? So he build up the angle to make the trajectory follow the plan, okay? So, and this happening every stand unless he gets to the 90 degrees. And now what is interesting in this black curve, which shows how much different NTVD he got. So you can see it from 22 to 16, which is like almost 6, even more like even 6, 7 feet, which is like almost 2.5 meters difference in TVD just because of this uncertainty. So you don't see it anywhere. It's not a difference between plan or fact or something. It's a difference between actual well, which you see on the papers, and actual well, which is located in the earth, right? So without this analysis, you would never see the differences exist. So by drilling these 300 meters, he already get almost 2.5 meters of error in TVD. So let's go next. This is horizontal section. So now he tries to keep exactly 90 degrees. So what's going on here? If you let the BHA drill in rotary mode, so it naturally drops the angle here. And what directional driller does? So he build up the angle just to keep it exactly at 90 degrees. And he does the good job, right? So this is what he's supposed to do. But actually, if you look closer here, so all the time you drill either 90 or more than 90 degrees, okay? So which actually leads you to the same TVD error. So during this another 300 meters of horizontal section, if we roughly look here, we have almost 10 feet of TVD error just due to calculation method. So in the building up section, there is an error. In the horizontal section, there is an error. and the range of this error is the meters. Okay, and if we look to the final well and delta in true vertical depth of the actual well position compared to calculated well position, you see it's almost at 6.7 meters. For the well with the 3 kilometers, it's 9,000 feet, almost 3 kilometers MD, not the deep well, with the huge TVD error, 6.7 meters. Of course, that's the published paper, so that's maybe this case can be a little bit extreme, right? Not every well is like this, obviously. But again, this conclusion here is to understand the range of this error. So the range of this error is in meters. So it's not centimeters or I don't know millimeters, it's a range of meters, which is really gives significant impact to the quality of our horizontal wells. So now, when you deal with the real environment, like imagine here you drill horizontal well from 3 feet from the top, right, in the oil pay zone, and you have water below and you have the shale above, right? And at one moment, the logs showing you that you exit through the top. And now you have to understand what's really going on. But it's in the real environment is really difficult because you have a combination of errors. So you have the geological uncertainties, so that can be the changes in the deep, and you have the geometrical uncertainties, which is the change of trajectory. So the case number one, yes, your trajectory may be 90 degrees and your top has changed the angle and you hit the top, or maybe the top is there it was, and you was drilling slightly up without noticing that, as I told you in the previous example, right? So you see the 90 degrees, every survey is 90 90 90 degrees, and then you see the hit the top. So and that because of the geometrical uncertainties based on the survey error and based on the survey method calculation. That's the current limitation of technologies we are working right now. Okay, so having all this in mind, so let's move to the economical part of the well. For example, now you see that having all those uncertainties is quite easy to lose part of the well outside of the pay zone, okay, if you don't use geosteering, any kind of geosteering, so if you just drill geometrically. So let's make this money exercise. So for example, you drill the well, and the total waste cost, so it's maybe fair for some regions in Latin America, so maybe slightly different, but it's good enough for exercise. So the total waste well cost to build the well cost to $3 million, right, from the top to bottom, with all the section, with drilling, cementing, with the completion, with all the operations from the beginning till the end. But horizontal section, which is this one, right, cost you 1 million, which is 1/3 of the well. When you drill it with the rotary systems, when you drill it with the LWD, so it's kind of expensive. And the section length in 650 meters. So now let's imagine that we just lost 65 meters out of 650, which is 10%. Okay. So now the question to you. So having lost this 10% of the horizontal section, how much money we just lost? Okay. So the first answer, like straightforward, can be okay. We just lost 10% of the 1 million right here. So just 100K, which is, by the way, is not cheap, right? But actually, if we think that for horizontal well, all the upper section and the linear conductors and all this and the reconstruction, so all this investment was done just to get 650 productive meters in the pay zone. And once you lose 10% of the production pay zone, which means that you just lost the 10% of the total well investment, which is actually 300K. So what can we conclude here? So number one, the horizontal section, horizontal well and thin formations is very sensitive to any errors and uncertainties, right? And it's also, each error is very expensive when you talk to the money. because you have to multiply your error to all the cost of the well, because you just lost 10% of your pay zone, you lost 10% of your production, and etc. etc. And here we're talking just about the capital investment to the well, right? Of course, we're not calculating the loss in production here, which of course will be much more severe in this case. Now let's have a look what's going on with the production here. Of course, to estimate the production of the horizontal well and to estimate the loss of the production is a quite a complex task for the petroleum engineer. Okay. It requires, of course, the hydrodynamic modeling and using, and it's depend of lots of factors, lots of depends on the formation, the pressures, the geometry, and etc. 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 So, and the right way to estimate the loss of production would be to use your hydrodynamic modeling and update the structural model inside this hydrodynamic with the microcells. So you have to reduce your cells as much as you can, so you can reflect the actual changes in trajectory. Because sometimes, let's say you exit your horizontal section is exit the reservoir and you lost like 50 meters of production, but by default in your aerodynamic modeling the cell has the size like 100 meters to 100 meters or 200 meters to or even more, right? So and also it won't even be sensitive to these changes, which is not right, because actually you just lost like 10% of your productive length. It's definitely will affect your daily rate. It definitely will affect your cumulative production over the years. So and it has to be considered. So the right way will be to do the the scaling, the right scaling. So around the horizontal well, the cells of your hydrodynamic modeling has to be as detailed as possible. But just for the matter of this exercise, so as I said, there are many different methodics and many papers, but just to pick one as a reference, you can look at this paper from the published from SPE, right? And some uh, graph here, how the oil well production rate depends on the horizontal well length, right? And of course, talking about horizontal well length, we're talking about the productive horizontal well length, which is inside the pay zone. Okay, so let's say for this particular exercise, so if you have horizontal section length with 1000 meters horizontal section, it's going to give you 10,000 barrels per day. And if you have, let's say, 800 meters, right, you're going to have almost half of this production. Okay, so you just lost 20% of your productive length and you lost 50% in your production. And you can multiply it to the life of the well and calculate the harm which you just get by losing the productive length. So, and also, as I said, this equation is not fair for every well, but you have to keep in mind that for almost every horizontal well, in some way the production will linearly or logarithmically depend on the productive productive um, productive land inside the pay zone. We also have to consider risk here, especially if we have water drive or gas cap drive reservoir. So where exactly did you exit? So let's say if you exit from the pay zone to the water, right? So now you will have problems with your production. Or if you get closer to the water and you will the well will be flooded more quickly than it was expected. Or in case of the gas, like the same problem. So it's the consequences of incorrect well placement can be much severe than it can be estimated from the first look. Okay, so it's definitely, as we discussed above, it definitely affects your capital investment. So if you lost 20% or 10% of your well, you just lost 10% of your capital investment. Next, if you lose 10% of the well, looking at this particular exercise, right? If you lose 10% of the well, so you're going to lose almost 20% of production here, of your daily production and the cumulative one. And also you can have a risk of earlier water flooding or gas cap or something else. So that's why this risk has to be considered very seriously. So the conclusion here. These days is really not efficient to drill horizontal wells geometrically, following the plan without any changes. Okay, so because we have a number of uncertainties, as we just learned, we know we have a few geological uncertainties, which has the quite big resolutions in the number of meters, and also depending on the system we're using for drilling the well, we have a number of geometrical uncertainties, which also have a significant range. Okay, so what to do? Solution. So number one, so we have to use the real-time appropriate technology. So we have MWD, we have LWD. So we can use these logs to mitigate the uncertainties and error. And how to do it in geosteering software, we will go to this little later. And of course, you have to do the real-time geosteering, which means when you see the environment has changed, so it's either due to geology or due to trajectory, you have to apply changes to the trajectory. So you follow the pay zone and you don't exit the top or you don't exit the water or something else. Okay. And we're getting here to the what is geosteering. So strictly saying, geosteering is an interactive method of drilling a well aimed to place horizontal section in the desired zone of the reservoir. And it has three main parts. Number one is technology. So it has to be the logging while drilling or measurement while drilling tools. It has to be geosteering software. So there is a number of different softwares right now in the market. It has to be personnel, which is geosteering engineers, which is very important because like the geosteering engineer can have a background of petrophysicist or geologist or even logging while drilling engineer, but he needs to pass the training. He needs to get some experience before you can call him the geosteering engineer. Right? So that's the kind of separate discipline, the geosteering and the geosteering engineer. And of course, you need to have a process, because if you don't have 24/7 process, if you don't have a proper reporting and you don't have a communication protocol that your decision is going to be executed like in inadequate time, so the technology and personnel will be just waste of resources and waste of money. So all three components are really important here to provide the geosteering service. Okay. And this is how the geosteering communication workflow normally works. So you have a geosteering team. So it can be the geosteering team inside of the client. By client, I mean the operator, the oil field operator, right? So it can be in-house team of the operator, or it can be a service company team which provides the engineers and the services. So whoever it will be, they make in 24-hour shifts, right? And they're looking constantly on the logs, they make correlations, and they issue the recommendations. So recommendation is going to the geology department of the operator. So normally the operator is the final one who has to approve it. So for example, if they say, we think that now the formation dip has changed and we're about to hit the top and exit the reservoir, and we think that now the dip is 0.5 degrees dipping down, and we suggest to drop the angle to 89.5 with the dogleg severity, let's say 3. Okay, that's the proper recommendation from the geosteering team. So it has to be approved by the geologist. So he said, yes, fine, I'm okay with that. And it also has to be approved by the drillers, because like the dogleg severity of 3 degrees, if it's fine in this case, or maybe we're going to have problems with the completion later on, or with the well cleaning, and a well condition, so it has to be approved by them as well. They say, okay, that's fine. We accept this severity and we're going to execute it as you requested. Okay, and the recommendation is going to be executed. And of course, these two teams is always has to be in constant communication to understand which which part is planning to do something, right? So to avoid any miscommunication and any problems of the well. So, but this simple workflow normally to work properly has to communication protocol. To make this workflow working properly, as I said, we need to have this document called communication protocol. So it's normally the protocol signed between the GI steering team and the geology and drilling team. So either inside one company, if it's everything is in-house, or between few companies like the operator and service company. And in details it describes how the decisions will be, how report will be prepared and sent to whom, daytime, nighttime, who will approve it. So what happens if the approver is not responding? Let's say it's nighttime and the chief geologist is not picking up the phone. So what they have to do, and etc., etc., etc. So this kind of document is normally a very detailed few-page document, which is like a vital to have the proper process on the GI steering well. And if everything is set up well, normally the decisions are made on bottom. So without any stopping and drilling, it's just like in a matter of minutes, it's issued, approved, and go into the execution. So it's how it should work normally. Okay, now let's move to the GI steering methods themselves. So we start from the basic one, which is called steering using synthetic log correlation, or in some other books it's called model compare update. So it's the basic method, and you just need one curve is enough to make this steering. So let's have a look how to build the model to be ready to steer, and how exactly we used those curves to steer. Okay, so first of all, we have to create the vertical section for GI steering, so-called curtain section. It's called curtain because as you see in the screen, so it has the section is follows the azimuth of the well, right? Which is not a straight line, but it's uh, straight vertically. So it has the shape of the curtain, right? And because the well in azimuth can be even has more changes, right? Can be like this, or can turn to the azimuth. So, and this vertical section will follow it, right? And then we have to cut it like you see in this screen. So we cut it based on the trajectory of the well, cut it through the 3D model, and then we flatten it on the screen. And this will call the GI steering section, or the curtain section for the GI steering. So let's have a look. Okay, so now we have our curtain section flattened to the screen, so we can work with it right now. This screen is the main screen for the GI steering engineer. Is the only screen you're working all the time. Okay, let me bring the pointer here. So what we have here. So once we cut this curtain section through our 3D model, we have a trajectory inside, and we have our markers, which gives us the pay zone here. Okay, so the vertical axis here is true vertical depth, and the horizontal axis here is the horizontal projection length. So that's the length of that low curtain border, which you've seen on the previous slide. So it's like was the curtain, now it's flattened. So this coordinate is specifically for GI steering. So it's a little bit different from what drillers used to call the vertical section. So this one is exactly for GI steering, called horizontal projection length, HPL. Okay, so next step here is to fill this curtain section with the property, with the formation properties, right? So we will start from the basics, from the gamma ray. Where do we take the properties? We take it from the offset well, which is the closest, more representative well we have, right? It can be few offset wells, so we can choose between them, or we can build the view curtain section if you want to refer one or another depending on what's going on with the properties. So let's start from the basic. So you have the gamma ray here. This green curve is the gamma ray. So you see that the high readings is the shale and the low readings is the sand. So we have the pay zone here, top and bottom, and our target zone. So what do we do right now? We propagate these properties through the curtain section, like parallel to the our well tops, our markers here, so-called surfaces. Let's call it surfaces, okay? So it can be propagated in parallel or it can be propagated proportionally. That depends on the geosteering engineer perception of the geology in this area. So in our simple case, it all be in parallel, right? So we propagate in these properties like this. Look carefully. Okay, that's it. So the high readings here represent the dark area here, which is the shale, the massive shale below the well top. And the low readings here represent the sandstone, and this light yellow, the bright one, is our sandstone, our pay zone. And this is our trajectory planned to be inside this pay zone, okay? So now we have the trajectory and we have the properties. The next step is to build the first synthetic log. So what is synthetic log? In our case, that will be synthetic gamma ray. So synthetic gamma ray is the how the gamma ray would look like if we drill the well using this trajectory and crossing exactly these properties at the layer. So once more, the synthetic gamma ray curve will represent how the gamma ray curve would look like if they cross this geology by this trajectory. So, and this like this, right? And it makes sense. So you can see here, while landing, we will have the high gamma ray here, and once we're in the pay zone, we see the low gamma ray here. So why is the difference here? Why we cannot use the vertical correlation? So it's kind of obvious. So when you deal with the vertical wells or the slant wells, you can just use the true vertical depth subsea correlation, and you don't need this sophisticated software. But in this case, look at this well. So all your log here will project just to one point to your vertical well. So the vertical correlations in case of horizontal well will be completely useless. That's why we use this horizontal correlation and the method called synthetic logs correlation. Okay. So now pay attention what will going on with the gamma ray as we change the geometry. For example, but just before going to the geometry change, I have added the resistivity curve as well. So you can see here now two synthetic curve, gamma ray, which is on the top, and resistivity, which is on the bottom. So you can also track the changes. So please pay attention that the color code is still gamma ray, okay? So we can see just one color code in the moment. But resistivity curve, if you follow the values, you will see that during the landing, we have the low resistivity in the shale, and once we have landed, we see high resistivity in the sand. So the next, we move into the geometry change. We're going to change the geometry of our formation, and we will see how it will affect the curve changes at the top. So, and this is what normally is done during the so-called pre-job modeling. Pre-job modeling is the geosteering engineer prepares the initial model for the geosteering. So it creates all the correlation, it creates the curtain section with the properties and synthetic curves, and then the geosteering engineer analyzes different scenarios. What happens if, for example, what happens if the angle will change just 0.15 degrees? And you can see that we're going to lose like almost 10-15% of the well if the dip will change only 15 degrees. But what is important? You can see the response of the curve. So obviously, if the dip change in the middle of the layer, we will already see the drop in the resistivity and some signature change in the gamma ray. So having a good correlation here, we can obviously avoid the exit through the top because we have like enough distance in measured depth to avoid the exit of the top. So now what's gonna happen if the dip will change in the opposite direction? For example, what's gonna change if with the dip will change to deepen up? Like let me do it here. So the dip is changing just 0.1 degree, just 1 decimal of degree. And you can see that we're going to exit to the bottom and we're going to lose almost half of the wellbore, right? And also you can see the curve response, not that obvious, but still you can see increase in gamma ray once we go down and decreasing in the resistivity. And what is important, the behavior of the curve look very different from when the dip is going to change up or going to change down. So now they know, based on this pre-job, right, that we can identify if the dip is going up and down, and this is very important because this is going to affect our decisions in the geosteering and the change in the trajectory. So let's analyze some other scenarios. For example, let's see what happens if, for example, we get the fault. Like in this case, additionally to the deep change, what's gonna happen if we will have a fault? Let's have a look. So you see, we have a small fault, relatively small fault here, just 3.5 meters amplitude throwing down. Okay, so the faults, this such as amplitude, is normally called the micro faults, and you normally don't see it on the seismic because it's below the seismic resolution. Okay, but look what's happened with our well. So having faced this fault, our trajectory is completely went out of the reservoir because the amplitude of the fault is bigger than the thickness of the pay zone. And normally such faults with small amplitude 2, 3, 4 meters will cause us lots of trouble during the drilling of horizontal well. Okay, and now let's have a look at the curves here. So can we see the fault on the curves? So in this case, yes, we clearly see the shift, the shift in change in the gamma ray, both gamma ray and resistivity. And this normally when we see during the clean fault from shale to sand or sand to shale. So okay, not every fault is that clean as this one, but normally we can see difference between exiting through the top, as we've seen on the previous slide, or exiting to the bottom, or hitting the fault. Okay, this is very important for us, and very important to understand if after we face the fault, if it was the fault throwing down or throwing up. Honestly, with the gamma ray only, it's not always the easy task, but in this particular case, we can see it clearly if the fault was down or it was up. So at this point, we finished this like simplified pre-job exercise. So once again, what we did, we analyzed different scenarios on practice, like how the curves would look like if the dip is going up. Can we identify that the dip is going up? What's going to happen if the dip is going down? Can we identify from the curves that the dip is going down? For example, at this point, if we would see that top and bottom is completely identical on the curves, so we would suggest to use some azimuthal data to just steer this well properly, so we can identify top from the bottom, right? We're going to talk a little bit more in the next part about azimuthal data, but in this case it's fair, like we can identify top and bottom. If we hit the fault, we can identify that it was the fault, and also we can identify it if we're above or we're below uh, from our pay zone, so we can make our decision. So now we finished our pre-job, and now let's move to the real-time stage. We will move into the stage, then the LWD curve will start to come during drilling horizontal well. Okay, now this is the interesting part. Look, before we had just black synthetic gamma ray here and black synthetic resistivity here. And now we start to drill the well. And now we start to receive the real-time actual data. So you see this red curve, and this is the actual real-time gamma ray from the bottom of the hole. And this is real-time actual resistivity from the bottom of the hole. Okay, and we see them on the same tracks with our synthetic curves. Now we get into the main idea of the synthetic correlation method. So the idea is very simple. Once the synthetic and actual curves are matching on the same track, like this zone, they more or less matching, which means our visualization of geology here is more or less equal with what is going on real time in the actual geology. Okay, so it means whatever we have modeled is confirmed. And then the curves are not matching, which means the geology requires some changes, and we have to change it unless the correlation will be accurate enough. So, like in this case, right, we're going to start the geometry of our curtain section to improve the matching of the curves here. Okay, for example, I did little shift. So you see the curves are perfectly matching here, but this like increasing separation. So which means is not possible to fix with the shift. Now is about so we have to try something else here, and we're going to play with the formation dip. Okay, by adjusting the unless we get the curves matched, you can see that in this particular area we had to move the TVD vertical shift just 0.5 meters and make a change 0.5 degree, just half degrees. And in this case, you can see that curves now reasonably match the Bose curves. And we have adjusted the geometry of our pay zone right now. And obviously, we see that the plan, having the follow the plan, we would exit the formation through the bottom, right? So we need to make the special adjustments um, to the trajectory so they keep it inside the pay zone. So now let's move to the changing of the trajectory, which is actually is the main part of the geosteering. Okay, so here you see that to keep the borehole inside the pay zone, we have to build the inclination to exactly 88.5 degrees with the dogleg, with the soft dogleg 1 to 2 degrees per 30 meters. Okay, now this is this red text is the main geosteering recommendation, which comes with the geosteering report and supporting correlation picture, and now it's ready to be executed by the directional driller. In the software I use, for example, we have this small trajectory planning tool, which allows to interactively place the trajectory inside the pay zone back. So you can try different scenarios. So you can check how many meters you would need to get back to the pay zone. So if you use the dogleg one, if you use dogleg two, etc., etc. So this is for you, for the geosteering engineer to play with the trajectory, and when it's ready, just to issue the recommendation. So to help him in planning, you can see this red cone. So the red cone is the visualizing dogleg severity. So in this case, as we said, the dogleg is 2 degrees per 30 meters. So which means the top and the bottom boundaries of this green zone is limited to this dogleg. So which means whenever I click inside this green zone will not exceed the limit of 2 degrees per 30 meters dogleg. So it's very useful to make the recommendation which will be more likely accepted by the drillers. So you don't exceed the limitations they have. Okay. So we have adjusted our trajectory, and as we requested, it was landed slightly above of the plane, and you see that now we landed in reservoir perfectly, right? We've been talking about that zone. So just one comment. So we split this well like for 3-4 big zones just for the simplify the process and to easily demonstrate it on the slides. But the process is going in real time, and the curves, real-time curves, are coming up every meter of the drilling at the same speed as the ROP is going, right? So, and the geosteering engineer can do as many changes as he thinks is required. So he can change it every, I don't know, 10, 20 meters of the trajectory. He can update the structure to get it more accurate. And whenever he thinks it's time to make a recommendation, so he do it. Okay. So now, till this point, everything is fine, right? But now we start to approach bottom again, and also the see that curves are not matching anymore. So which means till this point, this geometry is right, and after this point, something needs to be changed, right? And again, we have to go back to the geosteering tools and try to update the geometry so the curves are matching each other. Okay. In this case, we had to change the dip to make it dip down to 0.4 degrees, and you see that in this zone is the formation. Now it's almost horizontal, which is good for us. We're going to stay in the pay zone. Okay, so that's our objective, to follow the pay zone and keep drilling inside this sand. Okay, let's keep drilling and move to the next zone. So in this case, we have to, as we said, the formation is almost horizontal. So the recommendation will be just to build the inclination to 90 degrees and hold the inclination. So before the C, something will change. So we will keep 90 degrees in this formation. So let's move further. Okay, so now we have a new zone. And as you already know, till this point, everything is fine, is matching the picture we have here, right? The curves are matching each other, which means the geometry of the formation we have here is more or less accurate. Something starts to happen right here, right? And to adjust it, we're going to play with the dip angle again. So let me do it. Okay. Now we see the formation dipping down 0.6 degrees. And in this case, obviously, we have to follow the geometry of the reservoir, and we would recommend to drop the inclination just a little bit, just 0.6 degrees from 90 to 89.4 with the relatively small dogleg, 1 to 2 degrees per 30 meters. Okay. So now we go into the next zone, and you see like everything is fine. The declination is dropped, so the following the pay zone geometry. And now what happened here? So we see the sharp immediate change in both curves. So and we already know, and we already did this exercise in the pre-job modeling, right? So when we see such a change, it's obviously a fault. Now it's just a matter where to put this fault, obviously at this point, and to put it if the fault is going up or the fault is going down. Okay, so having this interactive tool, we can play with it and adjust. Okay, so we receive this fault, throw it down 3 meters, and now we obviously exit our reservoir, which now below, and we have to aggressively go down to chase our reservoir, right? In this case, the recommendation would be to drop inclination to 88.5 degrees, and now this time with the aggressive dogleg severity, which is 3 degrees per 30 meters, because we have to go back to our reservoir as fast as we can. Okay, so we did. So we went down, we found below our reservoir, and we landed again in this reservoir, and you see the curves are confirming it. Now we have good correlation, and we have low gamma ray, and high resistivity. So we lose just this little section, right, like 20-30 meters. We lost in the shale, but we quickly came down and recover our pay zone. At this point, the well is finished, and let's have a look at the result we have. Okay, this is the final correlation of the well, and you can see here the number called net to gross 92%. That's the main key performance indicator of the GI steering, called NTG or net to gross. So it calculates by dividing the net pay zone, so which means how many meters we have in our pay zone, divided to the total meterage of the well, and multiply the 100%. So obviously, if we didn't face any fault here, and we would keep all the trajectory inside the pay zone, we would have the 100%, right? So, but 90% is quite high KPI. So in given environment, so the well was just tuned very well, right? And what is interesting, you can check what would happen if we would follow the plan. This blue line, it was initial plan. So if we didn't do any changes, first of all, we would land in the shale below the pay zone, and we will drill all this meterage inside the shale, like 2/3 of the well almost. When we go in like the formation, now we would see the sub pay zone, and now we hit the fault, and the rest of the well would be outside of the pay zone, right? So this geology didn't have big changes, and still following the plan, which was okay at the moment we had it, would be catastrophic for this well. So obviously this well would be abandoned, and sidetrack would be required to re-enter the pay zone and provide the meterage inside it. Okay. Okay, now we're moving to the topic of geosteering using the azimuthal data, right? And to understand why would we need the azimuthal data, let's first of all have a look of the limitation of the non-azimuthal data. Let's have a look at this example. It's the real horizontal well, which was drilled a while ago by the geosteering team. And look what was happening. So from the first interpretation, it seemed that formation went up to 1.5 degrees, right? And that's why the landing was missed, and the trajectory passed to the shale just below the pay zone, right? And the engineers start to chase the formation to go back, and instantly the formation changed the angle to almost 5 degrees, deeping down. And he crossed the layer and get in the shale again, right? And the engineers start to chase it back, and he goes back, but instantly it found the pay zone, but it has the inclination of 1.5 degree again, and he like barely catched it. And the correlation, if you have a look, supports this. So we have a like pretty good correlation here, which supports the geology. But the post-well detailed analysis has shown that actually there is another interpretation, and this looks like this. Okay, and in this case you see the same excellent correlation, same correlation of the gamma ray and of the resistivity, but actually the formation was never deeping down 5 degrees. The angle was between minus 0.6 to plus 0.5, so it was almost flat. But once they missed the landing, right? They missed the landing. They confused the position of the borehole and actually was chasing formation which was already above of them, right? So we will get back to this case later on to see if we could do more with just two curves. But one of the conclusions here, it's obviously the limitation of the conventional non-azimuthal curves, because it can allow us to have more than one interpretation. So the same correlation can give us scenario number one, which we had before with the 5 degrees deeping down, and scenario number two, which has just between minus 0.6 and plus 0.5, right? The problem is because we don't know the angle here, so we just adjusting the geometry, but we don't know actually what was the formation angle, and that's the limitation of conventional non-azimuthal curves. Okay, and this is the mathematical explanation of what we just seen in the picture. So this is our layers. Let's talk about this blue layer for the beginning. Okay, the blue layer. It has three parameters. One is MDT, which is measured depth thickness. Next is the AST, true stratigraphic thickness, and third is the dip. And out of these three unknowns, we know only one, which is MDT, which you can see it from the log. And the dip and the true stratigraphic thickness, actually we don't know, right? And we can have a different number of solutions for this mathematical task. It's like for the same measured depth thickness and for the same true vertical depth, we can have different layers with the different angles and different thickness. For example, this blue layer have this measured depth thickness on the log, but the green layer, for example, it has bigger inclination, it has bigger dip, but smaller true stratigraphic thickness, and it will give you exactly the same log signature. The red is in the middle. It has the angle, the dip angle between blue and green, and the thickness between blue and green, and it gives you the same measured depth thickness. So which means when you're working only with the non-azimuthal curves, you limited you're limited by this environment. So you can have multiple solutions for the same log, right? And it's for you, for the engineer, to make an assumption. What exactly is my TST? So if you can fix your TST, if you know it from the offset well or from somewhere else, so you can fix it and then play only with the dip as we did in the previous example. But if it's not the case, like if it was changed in dip and in the thickness as well, so we're here like in a little trouble because we have lots of uncertainties here. So that's the mathematical explanation of this problem. So what do we do now? And what can help us is the azimuthal data, which is LWD images. So first of all, let's have a look at this open source video, which you can find maybe on YouTube. So you see that when you cross the formation, right, it has the sinusoid. And depending on the dip with which you cross the formation, the shape of the sinusoid is changing. So first of all, it's changing the signature. So it's looking like smile face or sad face. Like here you see, it's like so-called sad face because you cross it from top to bottom. If you cross it from the bottom to the top, you will see the smile face. So just looking at this picture, right, you can see if it's top or bottom. So without even calculating the angle. So it's very useful and it's going to help you in lots of cases. But the image actually has the dip in degrees. So if, as you see later on, we can calculate this dip value in how many degrees exactly was the cross formation to get this type of the sinusoid. So from this slide, you just have to understand how the LWD images will create it. It's like a lay down of the cylinder of the borehole. Okay, so it's lay down of cylinder of the borehole, and the let me bring the pointer. So, and the central quadrant is what was seen in the bottom, left and right what was seen in the top, and two lines in the middle is left and right. Okay, so we will see it on the next slides and the picture as well, so you can completely understand. But for here, to you to understand that the LWD image is the has azimuthal data, and it knows the formation dip, which we can use in our calculations. So the LWD image can be created from the different tools, from the different measurements. For example, it can be created from the gamma ray, that's the lowest resolution measurements, and from the resistivity, which is more high resolution, and from the density. Okay, so let's have a look here. That's how the quadrant is looks like. So the measurement, for example, in the gamma ray was taken in 4 quadrants, and the data was splitted like it's shown here. And then when you make a laydown, you see the 4 quadrants of the data. So let's repeat. So the gamma ray is the lowest resolution image. So normally it has from 4 to 8 quadrants. So some modern gamma ray tools can provide up to 16 sectors of the measurements, but still the quality is compromised because just of the physics of the measurements. Okay. The second by quality is going the density image. So the density image normally has 16 sectors, and it's like the quality is fair enough because the depth of the investigation and the resolution of this image allows to create this 16 sectors image. And the most I would say high resolution image right now from LWD is the resistivity, lateral lock resistivity image. So it can has 56 sectors, and the new tools can provide more than 100 sectors as well. So we will have a look at the example of these images on the next slides. For example, please have a look here and see the difference. So if you have 8-sector image, so 1, 2, 3, 4, 5, 8, all these 8 sectors have a laydown here. So you can see the quality of the data, right? The quality is not the best, but you still can identify when you cross the bad boundaries, when you see the pay zone, or you see the shell, right? And on the right track, you can see the image from the 16 sectors interpolated, and you see that it's more smooth and it's like more easy to read, and it's like more informative. So the more resolution of the image they have, the best interpretation we can get out of this. Okay. So for example, the images can have really different resolution. So the top one is still from the wireline. So the images can be created from wireline tools or from LWD tools. So from wireline, the best ones is called FMI, Formation Micro Imager, or UBI, ultrasonic borehole images. So these two is the most top resolution right now at the market. So it can show you the fractures, the secondary porosity, and the most of geological information, not only about boundaries, which we are focused on geosteering. So the resistivity LWD image is the best you can get from LWD, and you see it's like almost 2-3 times is the resolution is worse than the wireline. And when we move into the density image, and you can see it's like it's few times more big. And this is the interesting picture, right? You can see the wireline resistivity image from the left track and LWD resistivity image on the right track. And you see the more or less the same picture, right? The same features, but you see how much better resolution wireline has. Okay, at the same time you see this white stripes. So it's because the different nature of taking the images. For example, the wireline tool is not rotating during creating the images. It has the few pads, like in this case 1, 2, 3, 4, 5 or more pads, and between pads, and it's like scratching the borehole, the surface of the borehole with these pads, taking the measurements. And of course, between the pads, there is no measurements. So you see these white stripes then. But LWD image is working differently. It has one focused sensor, like in case of this LWD resistivity. It has one lateral lock resistivity sensor, which rotates 360 degrees. And while rotating, it's scanning the surface of the borehole, right, completely. And then when you get this laid down, you don't see any white stripes. So that's the big difference between wireline and LWD images. So that's another example of laid down images. So you can see here, then in this image, you see this green sinusoid. That's the bed boundary crossing, like here. Okay. So you see the cross the boundary from top to bottom, and you see this kind of a smile face. Then this vertical surface, that's the fracture, and you see these blue lines here, blue sinusoids, that's the fractures. So it's also very useful information, especially if you drill through carbonates and you want to know the fracture direction and the fracture quantity and quality of the reservoir. So the image can provide you. But normally you need to have at least the resistivity image to get the fractures, because very difficult to see it on a density image. At least the fracture is really like has a big opening. Okay, so again, the cross deformation and the fractures is what we can see from this type of the image. Moving to more examples here, right? Left track, you can see beddings and faults. So this is the bedding, and this is fault. So if you, as you already know, the fault has the sharp change in the curves and all the measurements, and it's the fault is almost perpendicular to the borehole. That's why we see this this type of the cross. So it's almost straight line, fault. Now this is interesting example. You see the formation, cross deformation, and you see the fracture, and you can identify based on the image if it's open fracture or it's a closed fracture. So if it's fracture filled with the mud or the fluid, that will be the one resistivity, and if it's filled with the cement, like a closed fracture, that will be different resistivity. It's also very valuable information for the production, for completion, and for geomechanics. And as I said before, you can also, in some reservoirs, you can see like cavernosity with the images, or you can see the secondary porosity. But for this, you need really high resolution resistivity LWD image. Okay. And this slide, you see the effect so-called well-bore spiralization, because once we take measurements of the image during drilling, the well-bore conditions um, can be different, right? Especially if you drill with the mud motor, the borehole can have some spiralizations, so it's not constant in diameter and it's not constant in its shape. And this kind of effect you can see easily on images, or if you look at 3D, right, you see this borehole spiralization. So why it's important? It's important to understand that this information is relevant for the drilling optimization and well borehole conditions, and it's also you have to consider this effect while you will be calculating the actual formation depth, because all this is like errors and giving some errors and uncertainties to our calculation. But just for your understanding, these visualizations, so how the real borehole can look like and how the good quality image can describe it. Now let's learn how we can read the color code of the image, because as you see it here, so the image is the color coded, right? And normally, if it's resistivity or density, it doesn't matter. For the high resistivity or low density, it's normally the bright color, and for low resistivity and high density is normally is a dark color. So, and there are two types of the scales of the image. One is the static, is when the colors are fixed. For example, like this, the darkest color is this number of the resistivity, and the brightest color is that number of resistivity, and it won't change during the image. So it's static for the entire well, I would say, or for the entire log. Or the second type of the scale, it's called dynamic image, like you see here. So we would need dynamic image scale if the changes is so small, or you wouldn't be interested to look at the particular interval, because sometimes the change is so small you don't even see the bed boundary, or you don't even see the fracture. So in this case, you can apply the dynamic scale, and it will automatically adjust the scale based on the interval. Like in this case, we have 25-meter interval, and the software automatically will identify what is the minimum here and what is the maximum here, and adjust the scale. So in this case, you would like more accurately identify some subtle small changes in resistivity or density, and you can see more features. But actually, during the geosteering job, you're going to need two of them. So you will need the normally you will run a static one to see the global changes, and you can run also dynamic one in parallel, so you can see the more features, and you're going to use them both together. Okay, so now let's move to quantitative parameters of the image. As I said before, from looking at the image, we can also not only see if we cross the top from bottom or from the top, we can also calculate the deformation dip in degrees. Okay, and looking at this picture, you can see that the formula is quite simple geometry here. So this is our borehole, which just crossed the formation, and this brown is our formation. Okay, and we just crossed, and this cross has generated the image, and actually the amplitude of the sinusoid of this image, as you see right here, will be the one part of the triangle, and the diameter of the well will be the second part of the triangle. And by resolving the simple geometry, you can calculate the angle. Okay, but you have to consider also the depth of investigation of the image. So actually, the layout of the image, it has the diameter of the borehole plus the depth of investigation. For example, if we have density image, the density image penetrate formation about 1 inch, which is 25.4 millimeters on each side. So, and to make this calculation correct, we need to add these values to the diameter of the borehole. And this is the formula, simple formula we have is arctangents of the this equation. Diameter of the well, in this case, it's 219 millimeters plus doubled depth of investigation. Okay, so here the symbol we get this side of the triangle. Okay, and then we divide it to the amplitude of the image, which is 15 meters, and this is in millimeters, and you get 1.2 degrees. Okay, so by every image, using every image, by picking this sinusoid, we can calculate the dip with which formation was crossed by this borehole assembly. Now let's look at the real example. So the software can do it automatically for you. The geosteering software can calculate these dips based on the image. All you have to do is correctly put the sinusoid. Okay, so if you see here, this formation cross tops is marked with the sinusoid, which is the green line here. Okay, and depending of the amplitude of this sinusoid and depending of how much is centered, the formation dip will be calculated. So you can see the few of them, right? 1, 2, 3, 4, 5, 6, 7, 8. So all these calculated here in the software, and every formation dip is marked at the curtain section. So, and you can see here how this information is represented. So every dip, each dip is going here as a short stick. Okay, and it's very useful for interpretation, so you can easily see what exactly is going on with the formation dip, especially if you have many of them. Okay, you could see the trend. So if the dip is going to change, or the dip is going down, or is going up. So in some cases it is pretty obvious. Okay, so this is how really it's done in the geosteering software, and this is how it's really useful when you have the formation dip, and now you have the more accurate interpretation, and you can avoid this I would say double possible interpretation, so you have the only one confirmed. Of course, LWD images and the dip calculated from these LWD images has its accuracy and has its uncertainty inside. Okay, and let's have a close look how exactly it's calculated, and what errors we can have. So first of all, let's remember from where we have calculated the dip, from which parameters. So first of all, in the formula we had the amplitude of the sinusoid, which is this one, okay? And but the question is, how accurate is the amplitude of the sinusoid? So we have the same image, for example, just slightly different processed and color coded, and you can see that in the left track the amplitude is 3 squares here, okay, and if you go to the right track is 1 2 3, it's almost 4 squares. So this is amplitude number 1 and this is amplitude number 2. So obviously it has some uncertainty, and it depends of the, I would say, eye of the interpreter, okay, how exactly you would put the sinusoid here. Second parameter is the actual well diameter, okay. So the actual well diameter is so if we have a bit size, and normally we put in the formula the bit size like 6 inch or 8.5 inch and etc. But is it actually exactly 8.5? So of course in the real life is not. So we have some variations, and to calculate exactly what's the diameter of the borehole in the current point, we would need to have a caliper, ultrasonic caliper, or some other sort of caliper to understand what is exactly. But when we put the diameter of the bit, of course we do some assumption, okay, and this also affects the accuracy of the dip we calculate at the end. And of course, the difficult question, the actual depth of the investigation. So we have a table, and we know like for each type of the image, for the density image, like it's 1 inch depth of investigation. For the resistivity image, depending of the sensor you have, it can varies from 1 to few inches as well. So we have this data, but in real environment, it has some variations, and it also affects the accuracy of your dip calculated. So for more details, you can refer to this paper. So, and the logic in this paper is very simple and straightforward. So they analyzed the error for each of the parameters in the formula, and then when you calculate your dip, you can insert these uncertainties, and you will get final uncertainty of the dip. And it's quite interesting, depending on the trajectory and depending of the which direction are you drilling. Is it close to the zone of exclusion of LW2 or it's not? Which direction, which azimuth? So all this matters here, and you can get the dip, for example, which is 2.5 degrees, and for this particular point, the error can be plus minus 2 degrees. So you have to be very careful with your dips. Of course, it's very useful information, and of course, if you have lots of them, it's showing you the trend, what's going on with the formation. But you have to be very careful with the absolute values of this dip. Okay, so they can be in some areas they can be quite questionable. Now let's have a look at the application of this technology to the horizontal well. So this is the actual geosteering screen from the geosteering software, which engineer is using to steer the well. And here you have all the measurements now, including the LWD images. And let's see how it really helps. So first of all, we have in the logged tracks here, we have gamma ray, which is red. We have resistivity curves, the propagation resistivity curves, and we have density and porosity. So neutral density and porosity here, which showing the quality of the matrix and the fluid. So this is typical triple combo combination, which actually very useful information. So in every meter of your well, you can understand is it exactly the pay zone, the saturation, is it oil or is it gas or water, and etc. And the bottom track, we also have a mud logging data here, and you can see this. The bright yellow is the sand, and this darker is the shale. So the combination of this percentage, you can see how we're going. So obviously the interpretation is quite easy here. Inside our pay zone, which is bright yellow here, we had a lot of sand, we have low gamma ray, we have high resistivity, we have high porosity and low density. So it's all obvious. But the problem is that the pay zone from top to bottom is almost identical. So if you go in close to the bottom or you're going close to the top, it's very difficult to understand from this kind of logs. So you can see it here, right? Almost no correlation. But likely in this case we have LWD image, which is density image in this case, 16 sectors density image with really good quality here, I would say. Okay. And now let's see how we're using this. So first of all, if you put this, if you would put this to the vertical track, you would see that in this zone you have only set faces, which means you cutting your pay zone from top to bottom. Okay, so you stratigraphically going down to your pay zone, and from this zone, for example, you see the smile faces, which means when you go from bottom to top, you cutting up stratigraphically your formation. So even looking at this data without calculating the angle in degrees, it's already very useful information to understand where you are. Okay, and also here the image dips were calculated. So all the sticks here see is the actual dips in degrees. And look how they help to identify the angle of the structure. So we can move the geometry of the structure following the dip, right, and understand where exactly we are. So with combination of the other curve correlation, this information is quite reliable. As you see in this example, the more information you have, by more information I mean more curves, like the gamma ray, resistivity, density, porosity, and the LWD image, the more information you have, the better understanding what really is going on in the formation you have, and you have more accurate and more useful interpretations, which allows you to take decisions in changing of trajectory, the decisions more accurate, which leading to the better well finally, right? As you see in this case, the well is 100% in the pay zone with the net to gross NTG 100% without even touching the top or the bottom. So this geosteering is like 100% accurate in this case. And now we're moving to the final topic of the measurements, which is deep directional resistivity measurements. And you will see that data can add even more value to your interpretation. And these tools are the top technology at the moment that LWD market has. Next topic is called geosteering using deep directional azimuthal data. And that's honestly like a new page in the geosteering for the entire industry, which has started in 2005 since the first deep resistivity tool appeared in the market. Okay, and together with this deep resistivity tool appears the concept which called proactive geosteering. So which means in contrast with the reaction geosteering. So reaction is mean when something has happened, like you cross the top or you cross the bottom, you have to react and you have to go back, which is good, right? Because you have reacted and you recovered your well to be inside the pay zone. But during this incident, you have lost certain amount of the productive land outside of the pay zone. So everything which was before 2005 in industry, so now called like the reactive geosteering, and having these deep directional resistivity tools, it's now the new let's say the new age of the geosteering, and it's called the proactive geosteering. So if talk about companies and names, the first tool was in 2005 from the Schlumberger, and then followed up, it was called periscope 15. Then the next was the Halliburton, was called ADR, azimuthal directional resistivity. From the Weatherford, it called guide wave, and from Baker Hughes, it was called deep track. Okay, so all this family of the first generation of the tools is was the beginning. So these companies, this big four, is now all of them have the generation, extra deep generation of the ultra deep generation of the tools, which I'm going to show you in the next slides. But now some independent company also came up with these solutions. So at least as far as what we know, it has the company called Oliden. It has the tool of first generation tool for deep resistivity, and company called Intec, which also has the tool on the first generation. Is what to my knowledge, right? So probably maybe some other companies also following up. So now let's have a look um, why we call this type of geosteering proactive geosteering. Let's have a look at this example, at this well. So we have a simple geometry here, simple geology. We have a top, we have a shale top which has low resistivity and high gamma ray, and we have the pay zone which has high resistivity. And let's try to drill it with the conventional resistivity tools. So imagine the angle, just for the reason of this exercise, the angle between the trajectory and formation is 2 degrees. Okay, just 2 degrees. And the distance to boundary at what you can pick the boundary of the shale. In the best case can be from 0.9 to 1.2 meters, so slightly more than 1 meter, right? So with the conventional resistivity tool. Now if you calculate what will be the distance of what will be this distance of these triangles, right? You will quickly see that once you pick this top, your bit will be already outside of the pay zone. So, and if you start to come back to your pay zone, so you go and lose the significant part of the well outside of the pay zone. Now let's take this deep resistivity tool. So as I said, ideally they can see up to 4 or 5 meters, but like in ideal environment. But let's take the average one, 2.5 meters. Okay. So with 2.5 meters, if we're able to see in 2.5 meters the top, so and we calculate this distance, that will be 71 meter before exit the top. So this distance is 71 meter before exiting the top, and this is more than enough to drop the inclination of 2 degrees. So even if you go with the really low dogleg severity, you can calculate yourself, right? Even if you go 0.5 dogleg severity, you will be able to steer the well smoothly and avoid exiting to the reservoir. That's the whole concept. So now you can make a decision before something happens. You can make a decision in advance. So, and imagine if this distance is 3 meters, or if this distance is even 4 meters, right? So you can have 100 meters in advance to take your geosteering decision and to make it smooth and softly, so you don't exceed any doglegs. Okay, so now let's move to the theory of this measurement itself. So the principle of these deep directional resistivity tools are based on the propagation resistivity physics. So the propagation resistivity tools, which are already in the market for many decades, so normally they operate on the frequency of about 400 kilohertz up to 2 megahertz, and they have depth of investigation is 45 slightly more inches, so maybe around 1 meter. So, and here is very important thing. So the depth of investigation of such tools is depend a lot on the spacing between receiver, as we have here, and the transmitter. And this spacing for conventional tools, as I told you, maximum, which like 40 with something inches, which gives us the depth of investigation slightly more than 1 meter. Okay, so what important was done in this new generation of the tools to reach the bigger depths of investigation? So the first tool which came up in the market, it was in 2005, and that was with the name of Periscope. Periscope was called at that time Periscope 15, produced by Schlumberger. Okay, so that tool had a depth of investigation up to 15 feet. That's why it has this name. But later on, it was proven that the tool can see even deeper, and that's why this number 15 was deleted from the name. So what was different in that tool? So first of all, they increased the depth of investigation almost to 4.5 meters. Okay, so the bigger depth of bigger spacing between receiver here and the transmitter, so the bigger depth of investigation. So very rough, we can say that the maximum depth of investigation in the best possible environment can be about 1.5 distance from receiver to transmitter. Okay, so in theory, if we have like 4.5 meters here, like in theory, in some high resistive, very contrast environment, we can see more than 6 meters. Okay, this number one. Second, they reduce the frequency, because the lower the frequency, the bigger depth of the investigation. So the lowest frequency before was like 400 kilohertz, and now they reduce it to 100 kilohertz. Okay, and the third and the very important modification to make the measurements azimuthal is to have receiver being tilted. So this receiver, you see, now it's in difference with the conventional propagation resistivity tools. So this receiver is a tilted, so is not aligned with the axis of the tool, and this makes this receiver sensitive to what's going on above or below or left, right from the tool. Okay, so these three modification is made a huge difference in the depth of investigation of the tool. Number one, increased spacing between receiver transmitter. Number two, reducing the frequency. And number three is tilted receiver, which make the data azimuthal. Okay, so this we're talking about the first generation of deep resistivity tools. So they all followed by Schlumberger, the Baker Hughes, and Weatherford and Halliburton. They also produce their tools for deep directional resistivity. So they all been able, more or less the same, to see to a distance of 4 or 5 meters. So the absolute maximum is something like 6. So that was the first generation. Now, in 2014, the market received the second generation of the tools, which was called extra deep resistivity tools. So, and what happened? Which modification they did? So they was following the same principle. For example, to get bigger depth of investigation, they had to put the transmitter receiver even more far away, one from each other. And in this case, to increase spacing up to 30 meters, they had to separate it in the BHA. So it's not one piece of tool anymore. So again, the first ultra deep directional resistivity tool was called Geosphere and was commercialized in 2014 by Schlumberger. So, and this tool had a separate subs, transmitter and receiver as a separate subs in the BHA. Like you see here, right? You can have the transmitter straight after your rotary steerable system or your motor, right? And then your receiver, when you can have the MWD, you can have LWD tool. Let me bring the the pointer here. See, this is the transmitter. So it can be straight after the rotary steerable system, after the motor. And then the different parts of BHA can be installed here, like the telemetry, like gamma ray, resistivity, density, whatever you need to look to your formation. And then you put receiver number 1, like here, as a separate BHA sub, and then you can have some other element, and then you put receiver number 2. Okay, so that's the simple idea. Of course, if you want to get even bigger depths of investigation, you have to put it even longer distance between transmitter and receiver. But that simple idea took like more than 10 years from the first modification to really start working, because it's really difficult task. So for example, the clock and this separate piece of BHA and receivers and transmitter, the clock has to be synchronized to the nanoseconds, and this separate patents was invented and produced to do this. And lots of different small things what was quite difficult to invent to make this all working. But finally, these days, also we have extra deep resistivity tools from each big service company, as not only Schlumberger, it's also the Halliburton, Baker, and the Weatherford. Okay, so remember, we have two generations. Number one is deep directional resistivity, up to 4 or 5 meters radius of investigation, and ultra deep directional resistivity, which is up to 30, 40 or more, depending on the resistivity environment of the formation. So let's conclude again. To get this result, you need to increase spacing between transmitter and receiver. You need to decrease frequency. By the way, the frequency of ultra deep resistivity tools can be as low as 2 kilohertz, for example. So if you remember, the first generation has 100 kilohertz, and now they're going even lower, like 2 kilohertz. So which makes the electromagnetic wave to travel to the formation even longer. And the tilted antenna, of course, to get the azimuthal data, because the data with such a big depth of investigation, which from even 5, 6, or 30 meters, will be absolutely not absolutely, but will be quite useless if we don't know from which direction it's coming from. Okay, so to make this technology work properly, it needs to have all these requirements built in. But this is just the first part of the solution. That's the physics of the tool itself. But also the big part is the so-called inversion. So the mathematic algorithm called resistivity inversion, which really gives the answer of what's going on into formation. So let's have a look what is this inversion and how we can use it. So how works this inversion? So inversion is the mathematical algorithm which resolving the reverse task. So let's say the direct task will be the forward modeling of the curve. So if you have a tool and you have environment and you're trying to model the curve, it's exactly what we did in the exercise with the synthetic gamma ray and synthetic resistivity on previous slides. So that process is called the forward modeling. But now, if we know the values of the curves and we know like the angle of the trajectory, but we don't know what's the environment of the formation, what is the resistivity. This is called the reverse task, the inversion. So what does inversion? It takes all the required parameters which measured by this tool, and as a result give us the resistivity exactly at the point that this tool is right now, and also, which is more important for geosteering, the resistivity of the formations which is above or below us. So let's have a look. So first of all, the inversion is calculated in the particular point, like here. This is called the measurement point. it located exactly in the middle between receiver and transmitter. So what's going on at this point? At this point, the tool generates the number of curves. So if we're talking about the first generation of deep resistivity tools, so it can be like maybe six, more or less 8 curves. Okay, if we talk which in the three frequencies, of electromagnetic wave. If we talk in the ultra deep resistivity measurements, that can be the 30, 40 or more curves, and it's not really possible to do any manual interpretation or to understand what's going on in the borehole just looking at the curve. We really need the mathematic, the machine calculating it for us. Okay. Also, the first tools had a deterministic inversion, which was based on the limited number of solutions, because in that year 2000 2005 the power of the and performance of the computing system was not that high. But the new generation of the tools using stochastic inversion, which means it runs like the 100,000 iteration in one point just to receive one solution. But whatever it does, inversion in stochastic or deterministic, the result is the same, is to understand what exactly is resistivity of the layer we are in, what is the thickness of this layer, and what layer we have above and below. Okay, like in this case. So the step of this calculation, it can be adjusted by the user, but normally let's say it's like from half a meter to a meter. Let's say it's 1 meter here. Okay. And in this particular point, we drilled 1 meter of horizontal well. And now we know that the resistivity of the formation which we are drilling right now is 20 ohm meters. We also know from the borehole to the top is the particular distance, let's say 1 meter, and to the bottom is 2 meters. And the layer above has the resistivity 4 ohm meters, and the layer below has resistivity 2 ohm meters. Okay, so what is different from this tool compared to all the others on the market? Because we know what exactly going on in the formation which we never crossed. So with the resistivity, conventional resistivity, gamma ray, density, and porosity, to understand what's going on in formation, we have to cross this interval. Okay, which means if to understand that we crossed the top of the reservoir, we have to cross it actually, which we don't want to. And this resistivity, these tools give us opportunity to see what's going on above and below or left, right from the well without crossing this layer. So that's why the geosteering using this technology, sometimes called proactive geosteering, which means we can do some modifications, we can do changes without even exiting the reservoir. Okay, so this, let's say, by the way, the first generation of the tool was limited just by one layer at the top and one layer at the bottom. The inversion was limited, and that made sense because the depth of investigation was not that big, and normally it's okay if they have one above and one below, and that was the limitation. But the new generation of the tool with the depth of investigation like 30-40 meters is not limited by that number, is limited by 6 or 7 layers. So if between these 30 meters you can have like 7 layers, the inversion will resolve it for you. But of course it's quite difficult, and you need to have the appropriate environment, and you need to have a big resistivity contrast. That's the important point, by the way. So the tool is working only in the formation with the high resistivity contrast. Like here, we have a contrast between 4 ohm meters and 20 ohm meters. So, and this boundary is easy to pick by the tool. But if we have like 20 and 21 here, so right, that will be kind of challenging. And also, it's important to remember that the tool, we're working with the resistivity contrast as an engineers, but the tool is working with the conductivity contrast, which means the conductivity is here is 1 to 4, and the conductivity is here the 1 to 20. Okay, and the higher contrast and in conductivity, So the easier for the tool will be to pick up the boundary. So let's move forward. That's what happened in 1 meter of drilling. So we drill 1 meter more, and you see like you have the new solution. Absolutely, it can be independent. In some inversions, it's completely independent. In some inversions, it can refer to previous result. So that's the big polemics between these scientists who is working on different types of inversion. And we drill more, and you can see it can be slightly different because, as I told you, so this resistivity can be not 4 meters anymore, not 2 meters, can be 1.5 or something, because each iteration to calculate the result is different here. And we have like drill 1, 2, 3 meter, 4, and 5, and 6, right? So you see like little by little, the tool and inversion creates the picture for you. And here you see like only 6 meter of calculation. And let's move to the scale of the well, and you will see like now it's like 600 meters. And this is the thousands of calculated point has to be calculated to give you this picture. This inversion can have different color codes, so but normally they try to use the more cold colors for low resistivity and more hot colors for high resistivity. So like in this case, you see the red here is the high resistivity of the Pozos, and then you have the shale here, which is a little colder color, the green one, and then you see the shale with even less resistivity, which is blue. And this particular case is quite interesting because we will be able to map the oil water contact here, okay? And it's all in the range. If you see in the scale, it's almost 20 meters depth of investigation. Of course, with such the information, you can place your well close to the top if you need close to the top of the reservoir, far away from the water, or far away from the gas contact if it would be here. So it's a different mode of geosteering. So you have much more freedom for solutions here, and you can be more efficient with drilling of this well. Or let's move to the next example, for example. That's just without oil water contact. You can see here how the high resistivity pay zone is mapped here with the red color, and then shale, and then shale with even darker, lower resistivity. Okay, so also you can navigate easily inside the formation without even touching top or bottom. With such a technology, you can navigate the wells in more complex reservoir. You can navigate the well with the longer horizontal section. So there are a few example of, for example, these wells being drilled in offshore with the 5 and 6 and even more kilometers of horizontal section. So in combination with the modern rotary steerable system and this proactive geosteering LWD tool, it can be the drilling can be really different. So it allows to drill the wells in more complex environment and even drill the wells without pilot holes sometimes, without any offset information. So you just go into the unexplored zone, and on the way while drilling you scanning the formation and adjust your trajectory, and also making the structural exploration. So this information can be also used and has to be used to update your 3D structural geological model after. Just to show you some latest technologies, because many times after the deep directional resistivity tools appeared on the market with such a big depth of investigation, most of the operators keep asking on every conference, like, guys, when you will present us ahead of the bit. So it's good to see long enough into formation, but we want to see ahead of the bit, right? And for many years, that question was silent, unless this interesting experiment came up from the Schlumberger tool. So that's the open source publication. You can find it at this link if you need more details. But the idea is the following. So they did the custom BHA. So they put the first transmitter, this one, not above the rotary steerable system, but below it. It required some modification to the rotary steerable system. It all was handmade just to get this prototype. But anyway, so they put the same ultra deep directional resistivity too, but the first transmitter was set below the RSS, just above the bit, right? And then the typical construction. So they have receiver number one, receiver number two. And what is interesting here? So once you have this receiver so close to the bit, you can see it here, that the part of the magnetic field travels ahead of the bit. Okay, and so now the signal is already there. Now is a matter of collecting the signal and a matter of correct interpretation, because interpretation, as we've seen before, is a difficult part in this kind of services. So here, horizontal interpretation was resolved by using inversion. So the inversion has to be modified to resolve this question. And look what we have. On the right side, there is the inversion result, but it's the different visualization. So it's not the same that was before. So all these vertical line, each of them represent the single inversion results. They all basically on the same axis. It's just a matter of visualization. So imagine the vertical well being drilled here, right? And the more closer it's going to the formation, the more accurate information it gets. For example, in this particular case, it's 30 meters from the bit to the layer. And exactly at this point, we have this result from the resistivity. So we already like 30 meters ahead of the bit. We start to see this conductive layer approaching. We're approaching. So, and then let's say we go in 29 meters here, and this is new calculation. So all these solutions actually in the same point. It's just a layout, so you can see them changing while approaching. So 29, 28, 20, etc., 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 15 meters. Okay, from 15 meters, like we not only accurately picking the starting from 15 meters, not only accurately picking the depth of the layer, we also the properties start to be more accurate, right? Because when if we go close and we cross it, we see that the actual properties are here. So in this blue color, which is the resistivity, like low resistivity value. So again, the experiment was quite interesting and successful. So the BHA, the tool started to see upcoming layer 30 meters ahead of the bit, looking down to the vertical well, and then we've been moving and get the more accurate picture. Okay, so the next I would say top updates on the technology is the combination with the seismic. So as you know, the seismic has the similar resolution than this deep directional resistivity field. So it's like in a range of 10, 20, 30 meters. And if using this information to reprocess the seismic attributes will improve the accuracy of the seismic lot, and they can forecast as well analytically ahead of the bit. Like look what's going on here. So that's the original top, the green line, okay, from the seismic. And during the drilling, the BHA was able to identify this actual top, this red one, okay. And this information was used not only to mark this top, but also to reprocess the attributes of the seismic for the entire zone and to get the more accurate picture. And this white is reprocessed formation top together resistivity with the seismic. And you can see here 120 meters ahead of the bit is already predicted the more accurate way. Look where is the the green one, which was old, and there is the white, which is updated. And they keep drilling and confirmed it right where it was forecasted. So it was very accurate. So with the accuracy of 2 meters in TVD, right? That's the huge success for this well. Okay. So again, to forecast even more ahead of the beat, it was used to calibrate it with the seismic. So also this top we have the 2D view, just look into the curtain section, but we also can use it the data from left and right, okay, from left and right, which was to make the 3D picture. And here you are, you can see the 1D longitudinal resistivity inversion, which makes you the 3D picture. Okay, so you can see what's going on up, down, left, and right. And this is very useful when you drill in the complex geology with the fluvial sand bodies, for example, with the resolution like 10 meters. And you can navigate not only by adjusting the dip, but also formation azimuth angle, but also adjusting the azimuth. Like look here. So to stay in this zone, you can also steer by adjusting the azimuth and keep the same TVD and avoid exiting the reservoir. So all you see here is you can check yourself with more details in these open sources, but this is the top LWD technology which exists right now in the market. So it's all aimed to improve your geosteering, to make your geosteering more proactive. So you can put to place the well in the sweet spot without in uncertain environment without any crossing top or bottom, losing any meterage outside of the pay zone, but also it provides the very valuable information for the 3D structural modeling, because all this information you updated here is the critical of this information. How critical and how useful is it? It's difficult to overestimate. So you can all this information is going to update your structural and property model and have it more accurate for the planning of the upcoming wells. Let's move to the next topic then, which is 3D structural model update in real time using the data from the geosteering curtain section. So let's see what's the workflow of such an update and what's the difference if we would do it in a simple way, so-called single point update and the multi-point update. So let's have a look. As you remember, so we started our preparing our geosteering curtain section from cutting it through the 3D geological model. Okay, so you can see here our curtain section, vertical curtain section, and here is already filled with the properties. And you see our trajectory and the 3D structural model, which we used initially to create our curtain section, right? The cross line between the vertical section and this 3D structural model was exactly our well top. So let's have a look how we can use the data after drilling to update the structure and make it more accurate. So that's the simplified look of the curtain section. So you've seen like we started the drilling from this geometry. So we at that moment we were thinking that the geometry of our pay zone is like this, so it's almost flat, and we planned our trajectory to be 90 degrees and to be landed and drilled inside the upper part of this pay zone. Okay, so that's the final curtain section we have. If you remember the well, it's the same well but without the fault we have. So we just finished the well and we have our surfaces, the top one and the bottom one, having different shape now from where it was at the beginning. Okay, but if we start to use the classic update method, in this method you get the new well top point only when you cross the structural surface. So we cross it once while landing the well, you see it here, and then we never cross again the top, or we never crossed again the bottom. Why? Because we did a good steering job and we didn't want to cross the top or bottom. Okay, so but actually if we move the structural surfaces based on one well top, as it's normally done without steering. So when you drill the slant or J-tap wells, A-tap wells, or horizontal wells using this method, once you get new point, you just update your surface based on that. Okay, which I will prove you on the next slide. In our case, is not the most efficient way to update the structural surface. So because we had many more points where we thought. So from the beginning, we use just one point to update because we have crossed our top here. But actually, we have all these points available here. So we have all this like unlimited number of points. I just simplified it, available to use to update this structural model. Okay, and the right way to do this, to use this point, will be like this. And in this case, you would get more accurate 3D geological model and use it for the more accurate planning of the upcoming wells. So let's have a look how we can do it in the geosteering software. And first of all, let's see the difference. So if you would do just one point update, you would get these structural surfaces, which I'm showing you right now. Okay, which is not bad. It's still more accurate when we had before, but compared to the more accurate surfaces I'm showing here, right, this is not exactly correct. So let's see how we can do it in the geosteering software. Okay, so on the left part here you see the 3D structure, and on the right part here you see the map. Okay, and let's have a look how it was before update in the upper part and after update in the lower part. So look here. So here we have the trajectory. We have crossed the 3D structural structural surface, and this red zone here is the new acquired information. Okay, so this red zone is the new information which we would like to use to update our structural surface, and so we do. So we kind of pull the entire 3D surface to match this point, and you see the difference in 3D before and after, and you see difference in the map before and after. You see this anticline like more extended to the north here. Okay, so that another view to the map before. Pay attention how the well is located here and how the anticline is located here, and after. Okay, you see this, you see the shape is touching the well here, and in 3D, that's the surface before drilling, the initial one. This one is updated using single point method, which is actually just shifted above, and you can see it, it's already better than it was before, but not that accurate. And next one is the surface updated using the geosteering software and multi-point update. And you see how more accurate the surface is and how more detailed the shape is. And if you're going to plan the new well here from this pad or here, so you can do it obviously more accurate using this updated 3D structural surface. And especially if you use one of the advanced logging while drilling methods, which is the formation images or the deep directional resistivity tools. So you get so valuable information for your real-time geosteering and to update your structure afterwards. And this information is actually mandatory to use this information to get more accurate structure, right? So and you can adjust your 3D geometrical and geological model, and you afterwards can adjust your hydrodynamic model. So in all your resources, it can be also adjusted to be more accurately calculated. Okay, so now let's move to the practice. So let's open up the steering software and create the project, steering project from the scratch, from the initial data, how it's normally done by steering engineer. Then after we created the project, we will upload real-time data. By real-time, I mean, of course, from the files, from the LAS files, but it will simulate the real-time process. Then we will correlate well, like in real time, finish it, and then we will do the 3D structural model update to see how it really works. So everything we described in the slides before, now let's go and apply in real geosteering software uh, by real tools. Okay, so let's move forward. So here we have the geosteering software, and let's start to create the project. We start from the creating the offset wells. First we load trajectory. Just make sure you have MD inclination and azimuth, the minimum required to be successfully imported for the both well, for the well number 1 and well number 2. Okay, so as you see here, we import trajectories, and we import now. After we have imported trajectory, we're going to import the logs data from the logs file, LAS file. So here we have gamma ray and resistivity, induction, log and resistivity. So we select both of them. So you can see the logs already there. And we do the same for the second well. Okay. Same gamma ray and same gamma ray resistivity. So we're going to work with these two curves today. Okay, let me just rename the wells, and then we will move to importing of the well tops, so-called markers. So you see we have two markers, top and bottom, for these two of the wells. So for each of well, it will be uploaded once you click OK. That's it. We have top and the bottom. That's our pay zone boundaries. Now let's create the correlation window and check the data we have. Okay, so I click well number 1, click well number 2. So I'm going to add the second track for each of the well, because we're going to have two curves, gamma ray and resistivity. Okay, so I add gamma ray and resistivity, and now I'm going to scale to see the data. Okay, and let's do a little formatting. For example, for the gamma ray, I will put it as a red and little thicker. Oh, sorry, for resistivity, the red and little thicker, and the gamma ray I will leave as a green. Okay. So now let's bring our markers here, top and the bottom. So you can see our pay zone. We just have to switch the to the vertical scale now. Let me do some color coding as well. So I put for the gamma ray some color scale, so it will be easier to correlate with the curtain section we're going to create in the next minutes. Okay, the correlation panel is ready. So now let's import our structural surfaces from 3D geological model. So this is the universal standards you can use. You can export it from any geosteering, any geology software you have, as a Petrel, Roxar, or Kingdom, whatever you have. You can export and import in the geosteering software. So we import top and we import the bottom. Okay. So having this imported, now we can create a map. Oh, sorry. Before that, I'm going to import the survey, the plane trajectory survey. So we're going to need it to see on the map as well. Okay, now we have it. So let's go ahead and create a map based on the top. So the map is ready. So it's already adjusted and color coded. So you can see I'm trying to bring my wells here and you don't see them because we didn't put the wellhead coordinates, and this is critical when you work in the maps in the 3D. So now I'm going ahead and put the X, Y, and altitude for each of the wells. So for the offset number 1, X, Y, and then altitude, so-called calibration elevation. Okay. Now you see the well is here. Okay. Let's do the same for the second well. So actually, you can avoid this extra step if you had a different template for the trajectory. So as you see, we imported trajectory first and then manually we put coordinates. But normally from the software like Petrel, you can export in a well format. So the file which contains already the trajectory and the wellhead coordinates. So you just drag and drop it here and that would be much easier. But for this project, we had this file. So let's follow these steps. Okay. So now you see the second well is there. And let's do it for the our planned well. Okay. Same X, Y, and then elevation. And keep in mind that the wellhead for the active well and for every planned trajectory is the same. So we do it just once, and all our planned trajectories and our active well will be on the same. Okay, now you see it well located. That's it. So we're ready to start. So let's have a look and 3D window. Let me click this top surface. Okay. Then let me bring my wells. And okay, so you can see it. Now let's do some adjustments so you can see the well top same as it was on the map. I guess it's just a matter of changing the step for the ISO lines. Okay. Yeah, let me. Just 1 minute. Yeah, so we're going to create the, let me create the curtain section now. Okay, so we choose the properties, the gamma ray, resistivity, and now we choose the offset well. It's going to be offset well number 1, and we go for gamma ray, and we go for resistivity. Okay, for the property propagation, we leave everything by default, so it's going to be proportional, no fluids at this time, and that's it. And let's have a look. Okay, the curtain section is created. Yeah, let's just scale it for the better view. Scale it so we can see our well, and let's do some formatting. Okay, so now you see our pay zone of interest and our plane trajectory. Let's do some formatting here. So first of all, let's adjust the color scheme so we see our pay zone better. Okay, skip it 15 to 20. Okay. And so let's just bring them to the same values from 12 to 32. Okay, now it's ready. Let me just scale it so you can see the pay zone and the entire plane well. Let's make it more visible. Let's make it blue color here. Okay, and let's make the surfaces a little bit thicker. That's it. Now let's add second track, as we have two curves. Gamma ray, resistivity. So I will just adjust the scale the same we have in our curtain section and in the offset well. So let's put it okay from 15 to 32. So let's adjust everything 15 to 32. 15, 32. Okay. And here 15 is. And now looks better. Gamma ray is ready. Let's move to resistivity. So let's keep it up to 50. Yeah, and that's fine. I would like to put a map here, which is going to be more useful. Okay, that's it. So the curtain section is ready for our pre-job modeling and ready for the real time. So now let's have a look at this curtain section in 3D. So as we've seen before, you see the curtain section is not flat, right? It has some shape like a real curtain because it follows the azimuth of the formation. See, it's more clear when you look at this in 3D. Okay, so it's quite useful to refer to 3D from time to time so you can see what really is going on and the map. Okay, so now let's go ahead and play with the geometry of our curtain section and see. But before I will create the copy of scenario so we don't fail the scenario we have here. So we create the second one and we're going to play with it. So the main tool normally for the geosteering engineer is changing the formation dip angle, and it's quite easy to do here. Just click this tool. You set your axis. 1 second. You just set your axis, which is the hinge point, and now you can change the formation dip. And pay attention to the curves as we've seen on the slides. See, as I move in the angle, and you see it changing here. Now it's minus 0.25, minus 0.24. So these small changes, we can exit to the bottom, and you can see how the gamma ray and resistivity curves would respond. Okay, and now I'm going to exit to the top, and also it's like 0.14, 0.15. So some minor changes can bring us to this exit through the top. And look at the curves, the response is different from the bottom. So which means even these simple measurements, gamma and resistivity here, we will be able to separate top from the bottom. So I do some modification in geometry, right, just to see how it will affect the curves. So during pre-job modeling, you can analyze different scenarios. You can sit together with the geology team and analyze what if angle change deep enough. You can also play with the uh, vertical shift. You can add some faults if you want. So whatever you think possible during drilling of the well, so you can try to do it. Okay. Once you've done enough this exercise in the pre-job modeling, we will be ready for the real time. Okay, let's go back to our main scenario and let's start to import the data. So in our case, the data is split in 3 big parts in the LAS file, but in real life, of course, it's going using VXML protocols or VITS protocols. It's going every meters. And even if the company don't have VXML, so the LAS file normally send every stand, which is like every 20 meters. Okay, now this red trajectory you already see is our real-time trajectory. So I make it more visible, more thicker. And let's load the curves. Yeah, you can add this well to the vertical correlation, but you will see soon how useless it becomes as more close we go into 90 degrees. Okay, so I adoptive rails, another track, same to be ready to load the curves. Gamma ray and resistivity. So let me do some switch to stratigraphic view, and let me do some adjustment. So basically we do the same format which we did before, just to the correlation to be easier. So let's bring the curves to the curtain section. We don't need this color code here. I will just switch it off right now. So let me adjust to the same scale. Okay. And the gamma ray, we don't need this color, so just disable it and we adjust to the same scale. Okay, and now we're ready to correlate. So we're ready to correlate, to change our geometry and make the correlation better. First of all, let's scale let's zoom it in comfortable size for us. And let's start to use the tools. Number one normally is go in the depth shift. So we do a little shift here as small as 1.6, almost 1.7 meters up. You can check this number, this box. Okay. So, and you see this correlation is in this zone, the correlation before the THL 1050 is fine. So we keep it and we put our hinge points here. And now we will change the dip. And you see how easy we can adjust. So actually, you can do some small modification. You can put some little hinge axis and do it to match exactly as you want, but it's not that useful during real time, because actually what you need is to get the angle change, right? Because all your geosteering decision will depend on the angle change. So if, as I said, if you want to be it more nice and make the perfect correlation, that's fine, but just not overdo this. So in our case, this accuracy is enough just to see that the angle has changed, and now we have to adjust the trajectory. And the trajectory has been adjusted, and we're going to load it, the second part of the well. Okay, so we load in the part of trajectory and part of the data. Okay, so next piece of information is now available. Okay, and you can see here it requires the correlation as well. So let's bring up our tools and let's play with the angle again. Okay, a little change. And we see that, as you remember from the slides, we see the formation is becoming horizontal. Okay, and that's why we're going to keep our angle close to 90 degrees. By the way, looking at this vertical correlation, let me just synchronize it. Okay, and you see, so we can obviously pick up the top here, formation top, and we can put this marker easily, right? But after that, once we get the high angle at 90 degrees, you see how useless the correlation is, because all the data is has the projection of the points, right? So at the drilling, so for the landing, this correlation was useful, but for the drilling horizontal section, is not informative anymore. So that's why we have to go and refer to the curtain section. Okay, let's have a look what's going on in 3D. So let's bring our actual trajectory. Let's make it more visible. And let's load the last piece of the data. Trajectory and logs. Okay, so you see the geometry is requires some changes again. So we're going to back to our geosteering tools and we're going to adjust it. Okay, so obviously that's the clear anticline here. So we've been expected a formation to be horizontal, and finally we get anticline. But look at these angles here at the top. So it's minus and plus decimals of degrees. So it's is really little changes in the angles we had. And again, look at the correlation. So it's not informative. Okay, back to our 3D view. And this red line is our new top of the reservoir. Okay, so a little in a minute we're going to update the 3D surface to match this. So I'm going to do two types of modification as we learned before. So first of all, I will do it using single point. Okay, let's go single 1 point. We modify and we get the new surface. So if you click, you will see this small change, right? The surface was pulled up. And now let's try the second option. Let's just a little change the scale so we can see it better. Okay. So let's just highlight our actual trajectory, real-time trajectory, so you can see this new zone of information. Okay. And then you see the new surface, how it really fits the new well top. Now let's make the second option, which is preferable one. So we update in so-called multi-point surface update. For that, we're going to use our geosteering scenario, right? So we will leave all the settings by default here and just click OK. And let's have a look at the new surface. So, and you see now it's much more accurate. So it's much more accurate and it's really fits the new information, the new well top we acquired. Okay. So let's look at it from different angles. Right, so obviously you see the difference, right? So how more accurate the second surface, and you can see it's in the map as well. So that's the default, that's the 1 point, and that's the multi-point. So obviously the multi-point update is more accurate than the 1 point update. So just look at it again from the different perspectives. Okay. So basically that was the simple workflow on the example of simple well we had. So we prepare the pre-job modeling. So as you've seen, is not that difficult from the data we had. Then we start to drill. So normally the well it takes, depending on the length and the formation, from few days to few weeks, right? The horizontal section, when you just load real-time data, you do real-time geosteering, and once it's done, you can do the 3D structural model update to make the initial surface more accurate. Okay, so that was the practical exercise based on the simple data, non-azimuthal, gamma and resistivity. So now it's finished, and let's move forward to more advanced methods we have. Okay, before closing the topic with the first geosteering method, with the correlation of synthetic curves, so let's summarize a little bit and talk about some hints and tricks while working with the non-azimuthal, with the conventional MWD, LWD curves. Okay, so let's have a look if we can do more with this data uh, more than we thought. Okay, so let's look again at this well, which we reviewed before. As you remember, this well was kind of difficult because we have here the excellent correlation. So you can check here. So we have an excellent correlation. So the gamma ray is the perfectly match, the fairly match the synthetic and actual MWD curve, and the resistivity, this purple, is uh, fairly match the synthetic resistivity curve. Okay, so but the problem is that finally, in the post-job analysis, it was identified that this interpretation was wrong. Okay, so if you remember this slide, okay, so this is the right interpretation. You still have the same fair correlation of the gamma ray here, and you still have the same good correlation of the resistivity here, but the geometry is completely different, right? So the structure which we've seen before was changing from 5 degrees to plus and minus 1, and in reality the structure was never changed even more than 1 degrees. It was just changing between minus 0.6 and plus 0.5. Okay, and actually the formation was missed, and the rest of the well was in the wrong zone. But of course, as the conclusion we did first time, the best solution would be just to add azimuthal measurements, and you will see how it can help us in the next videos. But we also could do more with this data here. For example, so this geosteering software that we've been using here allows to keep multiple scenarios. Okay, and if you keep so if you have a correlation which shows you that you're deep enough, just open up a new scenario and make a correlation. Try to make a correlation which is showing deep down. Okay, and you will end up one of two things. So number one, either you will confirm that this scenario is not possible, so you would not have any correlation at all, or like in this case, you would see that also has the correlation. And now we have two scenarios with with same correlation but with different geology. And which one would be the right one? So normally having the limited data, the simplest one is the most likely the right one, like here. Okay, of course there is more likely, there is more probability than the formation was changing in this case, just decimal degrees, then the formation was doing this crazy uh, syncline and anticline movements. Okay, so the bottom line here, the conclusion, the engineer had to use the different has to consider the different scenarios, had to try to make another interpretation during the drilling. It would be no harm. So he either would confirm that his interpretation is right because the other ones are not supported, or he would find something interesting and pay attention to different scenarios. And sometimes for a while the engineer has two scenarios at the same time. It's very common when you drill with only one gamma ray in the clastic reservoir, when you have the sandstone payson and you have shale above and shale below, and they almost identical. And in this case, for uh, some parts of the well, you can see that the correlation is exactly the same. You don't really know if you're going up, you're going down stratigraphically. And in this case, sometimes the engineer keeps two scenarios unless one will be confirmed and one will be discarded. Okay. Next, So let's have a look at this interpretation. This well is quite challenging because the correlation is very poor. So you can see here that this is gamma ray curtain section. The formation is very interbedded. So you see it's very interbedded, and the correlation is really poor. Look at the gamma ray, right? So it's not correlation. There is no correlation here. There is poor correlation here for the resistivity, okay? And the engineer was trying to correlate it as good as he can, but he couldn't. The poor correlation here, right? And you remember the reference data for correlation is this offset well, okay? But now let's have a look between the vertical correlation of these wells, and you will see that vertical correlation is poor as well. So once we cross the top of the formation, the gamma ray, and after this small layer with the signature here, the gamma ray is just don't have any signature here, right? So it's very difficult to understand on which part of formation you hear. So in this case, it has this layer and that layer, and in this offset well, it doesn't exist, and vice versa. And look at the resistivity as well. So it has two low zone resistivities, and now it's only one. So obviously, the formation has changed laterally. Once we stepped away enough from the offset well, the geology just has changed, and we don't have any more the correlations. What to do in this case? So particularly in this well, it's very useful to look at this part, because we just crossed stratigraphically almost entire interval, and all this information we have here. Why don't we use this information and this part of the well like as a virtual or pilot hole? So, and to make the correlation of well itself, so we correlate the next parts of the well one to each other. Okay, so now what we're gonna do, we're going to get rid of this offset well, and we put the data from this part of this borehole, and now we correlate it to itself, and you can see the correlation is much better. So it clearly all these markers are exactly there they have to be. So all this layer is confirmed, and the deep angle of the formation now is more accurate, and we can steer the well with the more confident. Okay, so the summary here: when you use the simple measurements gamma ray only or gamma ray resistivity, whenever it's applicable, always use the self correlation. Always use the self correlation well one del to each other. So in this case, I was using the steering office software, e-steering software, which is the main method here is the using curtain section, but it also allows you to do the self correlation, and you can also switch to the stratigraphic method. This method is more common for the unconventional drilling, for the like United States states land, all these shale plays and etc. When they drill with only one gamma ray, and they recommend to use stratigraphic method, which actually based on the correlation one piece of the well to each other. So we're not going to cover this functionality in this video, but is really has the same basics than the curtain section, but it's just to like I would say just to turn the tool from different way. Okay, so but anyways, don't forget to use this self correlation, and your probability of your success in the steering will be much better. So the summary, uh, it's recommended always, especially when you work with the limited set of measurements like gamma ray only or gamma ray resistivity. Always consider multiple scenarios, right? Try to use different offset wells if you have. Try to use different scenarios of structure behavior. For example, if your main correlation is deep in information deep up, just open up a new scenario and try to make it deep down. You either will discard this correlation after, because it's not it's not reasonable, or you will have another scenario, and this can help you later on. And always remember, the simplest solution is probably the more close to reality. Okay, and if applicable, again, as another scenario, like the first scenario, create a new curtain section and use self-correlation there, and you will see if your main scenario confirms or it's in controversy with this one. So it's really not recommended to stick to only one scenario in interpretation. Even you believe it the most accurate and you believe that's the best one, try to correlate opposite. Okay, don't stick to one scenario, is really dangerous um, to steer this way. And don't do the forced synthetic log correlation. As I showed you in the geosteering software, the tool is really allows you to make these micro sections and micro dips, and you can really correlate any part of the formation if you want to each other. Okay, and when you do the forced correlation, and this will confuse you in your geosteering decision. So it's not important to have the excellent correlation. It's important to have reasonable correlation, which will allows you to make the correct geosteering decisions. Okay, and now we closing the topic of model synthetic of the method of synthetic curve correlation, and we're moving to the practice in the geosteering software, but now in different set of data, working with the different project. So we're going to practice with the LWD azimuthal data images. So that will be in this case, the density images. So let's open up the software and look at the project.